So the goal of this video today is to give an introduction to organic acids. And to do this, we're going to talk about pKa, what exactly it is, and how we measure it, and what it's going to tell us. So pKa is a measure of acidity. So strong acids, like you are accustomed to, things like hydrochloric acid, almost always will lose their proton in water because they're so acidic. Now, most organic molecules are somewhat susceptible to losing that proton, but definitely not as much as hydrochloric acid. And we use the pKa scale to say how likely it is that that proton is going to leave the organic species. First, though, we're going to give a definition of what is pKa. So pKa comes from an equilibrium equation. And so if you'll recall, KEQ is products over reactants. And these are concentrations in water. So in acidity, we use Ka, which is the acidity constant. And this tells us about the strength of the acid. So let's consider perhaps the most common or prototypical organic acid, acetic acid. So acetic acid looks like this. And we can write an equilibrium expression of how likely it is to lose that proton in water. So we take here this acetic acid, we add it to water, and then we draw equilibrium arrows for the deprotonation of that proton plus H3O plus. And so here, KEQ, which is the Ka, is this. The products over the reactants. And now to get Ka from this, we assume that this is going to be constant. So at such a high concentration, because we're looking at concentrations in water, essentially the concentration of water is infinite in water. Technically, it's 55.5 molar. So we ignore that and write Ka equals, and in standard terms, BCH3COO minus H3O plus over the acid. And now for acetic acid, it is a weak acid. The Ka is 1.76 times 10 to the negative 5. And now this negative 5, that's really what we're concerned about. That is where the pKa comes from. So pKa is the negative log of Ka. So leaving all this here, anymore. Guess we'll get rid of it. Leave that. So pKa equals negative log Ka. So here our Ka is essentially 10 to the negative 5. So a high pKa will be a weak acid, and a low pKa will be a strong acid. So if Ka is small, pKa is large, and that's a weak acid. And if Ka is big, pKa is small, and that's a strong acid. So, kind of to put this in context, acetic acid, the pKa of that proton is about 5 because its Ka is negative 5. If we look at HCl, that H has a pKa of negative 7. And so that means its Ka is 10 to the 7. So it's huge. It's 12 orders of magnitude more acidic than acetic acid. Kind of conversely, if we look at just a regular kind of ordinary alcohol, so we'll look at ethanol, that proton has a pKa of about 16. And water also is going to be right around there. And if you look at, say, an alkane, so something like, this is hexane, this hydrogen here is going to have a pKa of like 50. So that means that it is 45 orders of magnitude less likely to lose that proton than our carboxylic acid, acetic acid. Okay, so now that we know exactly what pKa is, how can we use this? So pKa kind of tells us how likely it is in organic chemistry that the proton is going to be lost. So let's take a step back and look at that. So the pKa tells us how likely it is that the molecule is going to lose that particular H. So a high pKa, and so this is less acidic, weak acid, and kind of the flip of acid is a strong base. If it has this high pKa, it's not likely to lose that proton. If it has a low pKa, it's very likely to lose that proton. Low pKa, it's a strong acid. And so how this matters is you can look at equilibrium and try and decide if you're introducing a base into a reaction and you want it to deprotonate a specific proton. If you're using that base, say, as an initiator for a polymerization, by knowing your pKas, you'll learn whether or not that proton is going to be deprotonated and if your base is going to act in the way that you want it to. And so we can look at factors that influence acidity, and then we're able to predict pKas and predict equilibrium. So if you have a base, which proton is the most likely to be lost? Which site is the most reactive? So, keeping in mind high pKas are basic, low pKas are acidic, we can look at factors that influence acidity. And there are two major factors, and we'll call these Roman numerals 1 and 2. And you're looking at bond strength, which kind of is what it is, and then anion stability. And within anion stability, there are a number of other factors that we study in organic chemistry that can influence the acidity. And with these, they are atomic size. And so essentially, larger is more acidic. Lower pKa. Second one is electronegativity. So if you have a more electronegative element, it's better able to stabilize a negative charge. So once you take that proton off, it's better able to be stabilized in that negative state. And so that makes a lower pKa. Third one is resonance. And so we talk a lot about resonance structures in my organic chemistry classes, and hopefully you will too in yours. But basically, the more resonance structures that you can draw and the more good resonance structures you can draw, the more acidic and the lower the pKa. The fourth one is inductive effects. So if there's it's basically long distance electronegativity. If kind of down the carbon chain, there is an electronegative atom, something like fluorine, then you are going to have a more acidic species, a more acidic proton. I'll give an example of that. And then our last factor is hybridization. So in the orbital that the negative charge will be, if there is more S character, it's going to be more acidic. So let's look at some examples. So basically what we want to know is, let's say we have hydroxide and we want that molecule to act as a nucleophile or as a base to deprotonate a specific proton. Knowing pKas are going to tell us if it's going to deprotonate the proton that we want it to. So, erasing this top part, we can draw an equilibrium expression. And basically, when you're looking at the equilibrium, you're going to pick the side with the more stable anion. So returning to our acetic acid example, we have two deprotonated species. And so what we can look at is if any of these factors are going to contribute to anion stability. So in both of these, the anion is on oxygen, and that's a fairly electronegative element. But they're both tied since it's on oxygen in both of them. However, if we look at resonance effects, this carboxylic acid has resonance. And so this makes the anion more stable. Because the anion is more stable, we're going to pick this side of the equilibrium equation, and this side of the equilibrium equation is where we're going to go. We're going to see preferential deprotonation of the carboxylic acid. And if we look at pKas, this is going to confirm it. So the pKa of acetic acid we said was 5, pKa of water about 15. So that's good. To pick the side of equilibrium, to pick the more acidic species, or the more acidic conjugate acid, you pick the side with higher pKa. Equilibrium will lie to the side with the higher pKa. So we can look at another example like this. If we want to, say, consider, we'll look at ethanol. Plus an amine. We have this, and we can see that we're looking at electronegativity. So oxygen is more electronegative than nitrogen, so this anion is going to be more stable, and so equilibrium will lie over here. And if we look at pKas, this is going to be predicted there. So the pKa of this is about 16, alcohols are about 16, whereas amides have a pKa all the way up at around 35. Now we can take that one step further. If we want to deprotonate something on a carbon, that's going to be even harder. So with just that proton right there on ethanol plus our amine, remove that proton. We know this pKa is about 35, and this pKa is going to be about 50. And so if you introduced this carbanion in with a proton, no matter what other type of reaction you wanted it to do, if that amine was there, it would just take that proton, and then this would be your reactive species. So equilibrium would lie in this direction. And now there are many, many other examples that we can look at for this, and if you take my organic chemistry class, we will go through it ad nauseum, I promise. If you want kind of my handy-dandy table of what I think are the most important pKas to know in Organic Chemistry 1, and you aren't in my class, you can email me. It's ssidlick@cmu.edu. And if you are in my class, just feel free to ask me for this table. And so what this table is what I think is most important. And it has relative pKas. They're about right. Easy to remember pKas. And what we want to remember with these is just that the lower pKas, things like HCl, are more likely to lose that proton and act as an acid in solution. And then I include the factors that influence acidity for convenience as well. All right, so hopefully that helps clear up exactly what pKas are and how they can be useful in organic chemistry. Thanks for tuning in.